So in 1.8, we were doing limits, and we were working with trig functions, so we had kind of two levels of them. The first level just dealt with some basic trig rules that you need to remember because you'll be replacing things, usually in order to get something to factors. So if sine squared plus cosine squared equals 1, then you can replace sine squared with cosine squared theta minus 1, or 1 minus cosine. 1 minus cosine squared theta. You might want to do that if maybe you wanted a 1 plus cosine theta to cancel, because now you have a difference of squares. Same thing with cosine squared. Maybe you want to replace it with 1 minus sine squared theta, so that you can then factor that difference of squares and cancel. Tangent theta can be replaced with sine over cosine. Cosecant, if you wanted to, can be replaced with, and I say if you wanted to, because if it works, great. If it doesn't, you have to try something else. So these are all some basic trig identities that you learned in pre-calculus. All right. First of all, there is a typo on that one. So just like with all limits, the whole chapter, you always plug this in, because if you get a nice answer, that's your answer. And when I plug that in on the top, I end up getting a 2 pi. And I end up getting sine of 2 pi, which is 0. And then on the bottom, I just get 2 pi. And I can drop the limit because I have no more thetas or no more variables in my expression. And I get a nice 0 when I'm done. So remember, it's just that issue of 0 over 0 where we need to start messing around with some stuff. So the first thing I do on this one, again, I said I had a typo, is I plug that 0 in for theta. Cosine theta is 1, so the top goes to 0. Sine of theta is 0, so the bottom goes to 0. So what I'm seeing on the bottom there, and I am just going to do this one method since I'm recording here, I want to go fast, is I'm going to take the bottom of the fraction of the denominator, and when I see that 1 minus cosine on the top, I'm going to use the trig identity up here that says that sine squared is 1 minus cosine squared. Because then, my denominator is a difference of squares. And when I factor it, that's a cosine theta, by the way. I spit out my gum so I'm not munching in your ear. I now can cancel. And so when I re-plug that approach in, which would be my 0, 1 plus cosine 0 is 1 plus 1, or 2. So that limit goes to half. So on the top here, I'm just kind of doing what feels comfortable. I see the secant right here, so I'm thinking, all right, let's go replace that secant, because right now I'm sitting with 0 over 0 when I plug the pi halves in. And then I can make my secant 1 over cosine. And you might say, well, that's still 0, 0. It is 0 over 0, but we always factor, cancel, and then replug. So I'm going to factor and then cancel, and then I replug the pi over 2 in. So on the top, I'd have the 1, and on the bottom, I would have 2 pi when I plug pi halves in for theta. And I arrive at my limit. So again, on this one, cosine pi is -1, so I'm testing that out. But tangent pi is sine over cosine, and at pi that'd be 0 over 1. And again, sine of pi is 0 on the bottom. So I do have a top, or a denominator and a numerator, bottom and top going to 0 separately, which means this needs a little more work. Really, the only thing I can do with it is replace tangent theta with sine over cosine. In doing that, so when I do that, you'll notice what I end up having is canceling for a 1, canceling for a 1. I end up taking the limit as theta approaches pi of the function 1. and that limit everywhere is 1. So those are pretty straightforward substitutions that will lead you to an acceptable limit. And then we talked about 2 special limit properties, and I showed them this graphically, but just trust me, we arrived at 1 from both directions when we graphed sine of x divided by x, and we approach 0. So one of the first things to note is x must approach 0 for these. Anything else, you can't use this rule. On the next one, we graphed it, and this one ended up being 0. This is big star, for we're going to use it quite a bit. You'll eventually forget it, but that's okay. We'll have an easy way for it to come back when we need it. Little star in this guy. I think it pops up twice in these notes, maybe. Not a whole lot, and I didn't put that one on the test. Oh, the other note is that this expression right here really just means sine of the angle over the same angle. So it might be the limit as x approaches 0 of, say, sine of 3x over 3x. X is a placeholder, it's a variable. So that expression is of this form. It's the same angle in the argument of sine and the same angle on the bottom of the fraction. So that also will go to 1. So then we just practiced on the next page. So we went through and we said, well, first thing we have to do is plug that 0 in. E to the 0 is 1, cosine 0 is 1, 1 times 1 is 1. I'm at 1/4 and nothing fancy. So again, we don't always need something fancy. This next one, though, it looks a lot like the one that says the limit as x approaches, or any variable, approaches 0, of sine of some angle over, and it's not quite the same angle. It's not quite what I want it to be. So I'm going to do what in math is totally legal. I can divide by 4 and not disrupt the function as long as I also choose to multiply by 4. The limit of a product, which I have, the limit of a product is the product of the limits. It means I can do them separately and multiply them as long as they both exist. If I get a D and E for one of them, I can't do that. But the limit as theta approaches 0 of 4, or the limit as theta approaches anything of the constant horizontal function up at 4, not only is it 4 at 0, I could have approached anything. So that's a 1. So a lot of times, a 4. A lot of times what we'll say with limits is the constant can come out front. It is itself when you take its limit. So then, in my limit argument, I now have my new bestie when working with these trig limits, because we said on the previous page that that limit will go to 1 as long as you get the sine of some stuff over the same stuff, which leaves me with 4 times 1, or just 4. Again, direct substitution gave me 0 over 0 on this one, so I had to mess around with it. On this one, it gave me a nice 1/4, so I was done. So in box number 3 over here, 0 on the top and 0 on the bottom. I can't replace sine with anything. There's really nothing. It's not tangent. I can't replace that. But I will notice that I do have sine of some stuff. What I'd really like it to be is sine of 2x over 2x. So I'm going to create that. I technically have a fraction of 1/3. Their limits are themselves. The limit of a constant is that constant as you approach any numerical value. So that leaves me with sine of twice x over just x. But just like over here, I want it to be 2x. So I perfectly am allowed to divide by 2 as long as I then multiply by 2. And again, the limit of the constant is the constant itself. So it lends itself to 2/3 of the limit as x approaches 0 of sine of some stuff over that exact same stuff, which is our goal in that situation, because then it becomes a 1 and my limit collapses at a nice 2/3. So then I challenge them to do this one on their own, as you should as well. So pause the video and try doing this guy on your own. And what you're going to get is a 2/3 coming out front, because we don't like either of those numbers in there. We just want sine of 5 theta over 5 theta. So we are going to leave the theta down there, pull the 1/3 out front and the 2. So this guy's coming out front to get it out of the way. We'll divide by 5 and multiply by 5. Bring the constant out front, and then we'll have 10/3 of the one we like, which goes to 1, and my answer is 10/3. Okay, we're going to save that one. The next one looks a little weird. It doesn't have that sign in it, but it does have my cosine squared. I see that maybe I might want to, when I asked the class, I said, what's the only thing you really can do? And they said, well, pull a 2 out of the numerator. Oops. Then when then I started leading you through these. I just said, what do you see that you can do? If it doesn't work, we'll redo it. Somebody said to replace that 1 minus cosine squared theta with a sine squared of theta. Yeah, that'll work. And then hiding in here, we saw that, I'm going to run into this problem here. So hiding in there, we did have the sine of theta over theta. We just also had an extra sine theta. So just stare at that and convince yourself that what I wrote here is equivalent to what I wrote here. And again, I'm skipping some steps because the videos, they do tend to go a little faster, but the 2 comes out front. This one goes to 1 on its own. And again, we can split that product up into its 3 pieces, the limit of 2 times the limit of sine theta over theta times the limit of sine theta. I'm skipping writing that all out. You think of it as 3 different pieces. As long as they all exist separately, you can multiply them. So 2, its limit is 2. Sine theta over theta, we said, goes to 1, which basically leaves me with the limit as theta approaches 0 of sine theta to be sine 0, which is 0. This is one where we got it 0. We actually did that one 2 ways as well. We factored this guy into difference of squares, and then we ended up having that second trig one that goes to 0, but we don't really need to do that right now. So in this situation right here, I paused and I said, you guys, think back to elementary school. When you have 2 plus 3 over 7, that was actually adding the numerators and keeping the common denominator. You are used to given this and saying add, and you say, oh, common denominator is just 2 plus 3 over 7. But when you have this shape, I say that makes a heart, you can break it apart. You can also split it up. So this one right here, again, is sort of a mess. But when I rewrite it, I'm going to be able to do some canceling. So I'm going to write and take the heart, I'm going to split it into its 2 pieces, which would be theta cosecant theta. Actually, on this one, truth be told, they told me to replace the cosecant with the 1 over sine, and we went through the whole process, and then I showed them this shortcut. So on this one, I'm just telling you, a lot of times when you see this heart like that shape, you can break it apart. What this becomes is the limit as theta approaches 0 of basically 1. Right? Gone. Plus the limit, again, I'm going to show this one be broken apart, not just by my words, but in actions here as well. So remember that cosecant can be written as 1 over sine. So on this one, I end up with theta here, and then the cosecant puts a sine theta on the bottom. But when I multiply that by the reciprocal, it ends up being sine of theta over theta, which we said is our new bestie, and it goes to 1. So this is the limit of any constant is itself, and both of those will have a grand total of 2. So moving right along here in the next one, what can I do? What do I see that I can do? I can factor out a sine. It also makes a heart, and I can break it apart. So there's often several ways to start and several ways to arrive at the correct answer. But my gut sees that. And then look at what I did on the bottom there, because I was trying to, again, find that new limit property that says this goes to 1. The limit of the product is the product of the limits. Separately, the one in black goes to 1. The one in red, I'm going to put in blue here. If you look on the previous page, that's the one that I said won't pop up much. Never on the test, once or twice on homework. So we're just going to go throw that one out there. Okay, so we have those 2 new properties. I'm going to go back to them again. We're trying to break up our trig expression to maximize that this can be replaced with a 1 and this can be replaced with a 0. So we're trying to, for lack of a better term, we're trying to like suck them out of the problem. So they were pretty good at this by this time. So I got on this one, I said, do you see either of those new limits in there? And somebody said, yep, they saw that second one right here. And I said, well, you're allowed to break apart those sums and differences. So I'm going to go 1 minus cosine theta over theta. I'm going to pull that out so I can visually see it. And then it would be plus sine of 2 theta over theta. Convince yourself that those are the same. If I add the numerators and keep the denominator, I'm right back to the original expression. This one goes to 0. It's my new one. This one, again, it's not quite what I want. I'm going to put the limit on this one as well, just to show you doing them separately. I would say I would love to have a 2 down here. I have to balance it out, then with multiplying by 2, limits of constants are themselves or they come out front. So that one ends up being 2 times my new favorite limit, the sine of some stuff over the same stuff. And that one arrived at 2. And then my last challenge for you is to try this one on your own. So pause the video and then come and take a look at it. They did a row check. So I had them kind of check in their row. Once they were sure everybody in their row had it, we moved on. So again, separately, and I skipped that on some of the ones up there, just make the notes go faster. I do have a numerator and a denominator going to 0, both, or separately, which means it needs more work. Now, this isn't one of those basic trig substitutions because nothing gets better up here. But I do see this heart shape. So my first line of attack, and I'm not dropping my limit, I'll keep this last one really nicely notation here. So I'm going to break the sum apart. It makes a heart. You can break it apart. The limit of a sum is the sum of the limits. We can do them separately as long as they both exist. 2x over x is just 2. We cancel first before we replug. And then I do plus the limit as x approaches 0 of sine of an angle over that very same angle. So when I'm all done, I have my constant y equals 2, and as I approach 0 from both sides, that's up at 2. This is my new favorite replacement limit. It goes to 1, so hopefully you got a 3. And then the assignment was worksheet 1.8. Peace out.